All right, so we are picking up with the rest of lesson 4.2. This is on particle motion, so talking about velocity, acceleration, all of those things. In example 2, we're looking at a velocity graph, okay? That is probably the most common scenario where we're going to show you a graph of the velocity of something and then ask you all these questions about it, okay? That also probably aligns with what you've done in physics so far. So I would actually recommend to you, if you haven't done this yet, pause the video and see how you can do with answering these questions on your own first, and then restart the video and kind of follow along with me. So first it says just describe what's happening in terms of time. I think I'll kind of do that as I answer the rest of the questions, so just to save you a little bit of time. So let's just start here. The particle's velocity at 5 seconds. Well, this is the velocity graph that I'm looking at. So if it's asking me about velocity and I have velocity, I'm just reading that right off the graph. I'm just going to 5 seconds here and reading straight down, and I'm seeing -3. Okay, so I would say that the velocity at 5 seconds is -3. This is in meters per second. Okay, so just reading straight off the graph there. What is the particle's speed then at 5 seconds? Well, remember, speed just doesn't care about the negative here. So the speed at 5 seconds, I would say, is 3 meters per second. So just to clarify, what we're saying is happening right here is the object is moving in a negative direction. So that's probably to the left, okay, or down, depending on what the scenario is, right? Moving in a negative direction at 3 meters per second. Speed just doesn't care about the negative direction piece. Okay, when is the particle at rest? At rest is when velocity is equal 0. That would be anywhere along the x-axis. Now, there's a couple of pieces of this graph that I'm not sure you can see really well. First of all, I believe right here at the beginning there should be a little horizontal segment that is entirely on the x-axis. I think that same thing happens down here to take us to that 20 seconds. I could be wrong, but that's how I'm going to answer my question. Okay. So we're at rest everywhere from 0 to 2 seconds. So I'm going to say from 0 to 2. And then I have a real quick moment where I pause and change directions, right? That's what's happening here is I'm changing directions from negative to positive. And that we're going to say is about 6 seconds. I think I'm rounding a little bit. Happens again right here at 12.5 seconds. And then at the very end, I'm going to say from 19 to 20. Now, if you looked at that and just said 19, I totally get it. That's okay. So when are we moving to the right and to the left? So that's talking about direction, right? So that's positive versus negative velocity. So all of this up here above ground, positive velocity, that's when I'm moving to the right. Everywhere below ground, that's when I'm moving to the left. So let's see where that actually happens. I'm only moving to the right for this little chunk that looks like a trapezoid. So I would say I'm moving to the right from 6 to 12.5 seconds. And I'm moving to the left essentially everywhere else. So I'm going to say from 2 to 6. And then again from 12.5 to 19. Okay, what is the magnitude and direction of the particle's acceleration at 15 seconds? So just so you know, magnitude and acceleration just means give me a number and give me a positive or negative sign. So essentially, we're just going to find the acceleration at 15 seconds. Okay, so 15 seconds falls somewhere on this little line segment. I don't need the value, right? Because that would be finding the velocity at 15 seconds. The acceleration is going to be the slope, right? So I need to figure out what is the slope of the tangent line right here. I could only really ask you this question if it's a straight line where you can find the slope yourself, right? And so what I'm going to do is I'm going to look at the endpoints here of this little segment. I'm going to look here and I'm going to look here. And I'm going to do rise over run. Now, in some graphs, you might just be able to count it. This is a little bit hard for me to count. Old lady eyes here. So this point here, I believe, is at, oh, I hope that's -6. So that's at 14, -6. And this point up here is at 16, -2. So my slope would be, I guess I'll have to do this down here, y2 minus y1. So -6 minus -2 over x2 minus x1. So 14 minus 16. That's going to be a -4 over a -2. So that's a +2 for my acceleration. So I would say A of 15 is +2, and this would be meters per second squared. Okay, so let's talk about that 15 seconds here. What is actually happening here? Well, my velocity is negative, right? So I'm moving in a negative direction. I'm going to kind of just make a note of this. We know we're moving in a negative direction. Okay, but we're heading back towards that x-axis, right? We have a positive acceleration. And these two things together mean I'm going to be slowing down. Okay, so now let's see which one of these multiple choice options matches that. Slowing down, so I'm down to B or D. And in a positive or a negative direction, that would be a negative direction. So it should be letter D here as an option. Okay, so now let's look at 6.75 seconds. So this is 6, so 0.75. I'm guessing it's talking about right here at the corner. Okay, could be off just a little bit, but I don't think that's going to change our answer. So up there, I have velocity that's positive, so I'm moving in a positive direction. Okay. My acceleration, I mean, if I'm on this line segment, I'm going to have positive acceleration. Because I don't see an option that talks about, like, you know, this would be a 0 acceleration right here. This would be my rate of change is not changing. Okay. I'm still moving, right? But I'm moving at a constant rate. So I don't see that in here anywhere because I wouldn't be speeding up or slowing down. So I'm going to assume that this wants me to talk about positive acceleration. These two things together mean that I'm speeding up. And so speeding up in a positive direction would be letter A. Okay, let's head on to the back page here. One more page of notes here, and this does get into some new terms, some new concepts. First, we have this term displacement. Okay, displacement, net change in position over an interval. I am going to make a note here that displacement, the flip side to that, the kind of the opposite of that, would be total distance. So it's not the same as total distance. I'm putting it there for comparison. Okay, the verse. We're talking about like displacement versus total distance. What's the difference? Okay, so let's say that an object starts here and it goes up and then down and then up and then down and up and then down and up and down and it ends here. Displacement only cares about the distance between where it started and the distance between where it ended. So let's just say that that's about where it ended. Okay. The displacement would say, what's that distance right there? Okay. What's the distance between the starting place and the ending place? Okay. Total distance is going to add all of this distance together. It's going to add the positive and the negative and the positive and the negative and the positive and the negative and so on and so on and so on until it tells you how far did this thing actually travel. Okay, so displacement kind of disregards all of those changes in direction and just looks at start and stop. Total distance adds all of it together, and we're going to have to talk in a minute about how we're going to figure that out. Okay. But for displacement, basically what you're going to do, if you're looking at an interval, let's say our interval is from A to B. To find the displacement, man, I did not write this out well, but to find the displacement, what we're going to do is we're going to find the position at the end of the interval and subtract the position at the beginning of the interval. So we would find where did I stop? Where did I start? And then subtract these two things to figure out what that distance is in between them. Okay. For total distance, we're going to have to do like a bunch of little displacements. So what total distance is going to do, and you'll see this in this example down here, is basically I'm going to find the displacement from here to here. And then I'm going to find the displacement from here to here. And then the displacement from here to here. And so on. And then I'm going to add all of those little distances together. So that gets a little harder. I probably wouldn't give you one that's this crazy, but you get the idea. Okay. The next two that I want to focus on, these are super commonly missed problems. So make sure you kind of tune in on this. If I ask about the average velocity, this is going to be an average rate of change, but it's not the average rate of change of the velocity. Okay. Velocity is the rate of change of position, right? Okay, because that's what velocity is. So when I say I want the average velocity, what I'm really asking you for is a rock, but of the position function. Okay, so average rate of change is going to look something like this. I'm going to go x sub b minus x a. This is the position function, would be x of t over b minus a. Okay, a rock. That's all this is. Average acceleration, let's use kind of the same reasoning here. Acceleration is the rate of change of velocity. Okay. So when I ask you for average acceleration, I'm asking you for a rock, but of the velocity function, not of the acceleration function. So average velocity is going to look like, or average acceleration will be a rock with the velocity function. So I'm going to do v of b minus v of a over b minus a. We'll talk about that some more with this example here, but just know that this is a super common mistake I see people make. When I ask average velocity, they almost always want to use the velocity function. And remember, you're looking at what is changing when you're talking about velocity. It's the position that's changing. Okay, so we're going to do this one entirely without a calculator. Okay, so I'm going to demonstrate for you how you would do something like this without peeking at a graph, without looking at anything. If we have time, I might pull up a graph at the end so we can just kind of verify everything. But I want to show you how to go through this like without a net here. Okay, so first it just asks for displacement over the interval from 0 to 2. So what I want to find is the position at 0 and the position at 2. That's the s function. So I'm going to say s of 2 equals, that would be negative 2 squared plus 2 times 2 plus 3. So I'm just using that original function exactly how it was given. That's negative 4 plus 4. So that's 0 plus 3. So this is 3. And then s of 0, this one's going to be interesting. That's going to be 0 squared plus 2 times 0 plus 3, which is also going to be 3. So displacement is how much did this change, right? So my displacement is just 3 minus 3, which is 0. So based on displacement, this thing didn't move at all. Right? It started and stopped in the exact same place. So that's what we're saying our displacement is. 0, I don't know, again, I didn't give units here, so I'm just going to say 0 units. Okay? So now let's talk about total distance, because that's going to be different than displacement, because we don't know what happened between 0 and 2 here. So the first thing I want to find, this is going to be kind of similar to the first problem we did in the first example. I want to find where does it change direction. And then I'm going to find displacement on the intervals where it's moving in one direction or the other. So the first thing I want to know is when does the velocity equal 0? Well, I guess for that I'm going to need a velocity function. So let's see, that would be v of t is, I guess it would be v of x because we're using x here. Negative 2x plus 2 The 3 goes away, and I want to know when will this equal 0. Subtract the 2, so I get negative 2x equals negative 2. And this tells me that that's happening at x equals 1. It's really convenient that this happened kind of halfway through this interval. I wouldn't count on that always happening. I think I've given you a nice, easy interval with some symmetry in it. And I do that a lot when I'm making you do things by hand, okay, where things aren't so ugly. But don't count on that. You can't assume that this is always going to be right in the middle. Okay, so I want to look at the interval from 0 to 2. And I'm going to put a dividing line in here at 1 because that's where this thing is changing direction. So what I need to know is how far did this travel from 0 to 1? And how far did this travel from 1 to 2? Okay, so I already know my position at 2 and at 0. So this up here is talking about the s function. What are my positions? My position at 0 is 3. And my position at 2 is 3. Let's figure out our position. So now we're going back to the s function at 1. Okay. So just real quick, s of 1 would be negative 1 squared plus 2 times 1 plus 3. Be really careful with the way this negative sign is. This gets applied after the square, the way this is written. So 1 squared is 1. This makes it negative 1. Negative 1 plus 2 makes positive 1, right? And then 1 plus 3 gives me 4. So this is a position of 4. Okay, so now how far did we move? Well, to move from 3 to 4, we moved a distance of 1 unit, right? To move from 4 to 3, technically we could say that our displacement is negative 1, okay? But when I'm talking about total distance, I don't want anything to be negative. I don't want to talk about, like the reason this came out to be 0 is because 1 and negative 1 makes 0. But this is still a distance of 1 unit, right? So the way I find my total distance is I take those little mini displacements and I add them together, but I ignore any negatives. I use absolute value. So really what I'm doing is this. Absolute value of 1 plus absolute value of negative 1. And that would be 1 plus 1, which is 2 units. So displacement shows that I didn't move at all. But total distance, I actually moved 2 units. I just moved up 1 and down 1 and landed back in the same spot. Okay, so now average velocity. And I would really encourage you to do this exact thing I'm about to show you every single time I ask you this question. Average velocity. Velocity is rate of change of position. Okay. So what I'm really asking for is a rock of the position function from 0 to 2. We actually should already know the answer to this based on this up here, but we'll figure it out. So I would do s of 2 minus s of 0 over 2 minus 0. Well, we did this s of 2 minus s of 0 up here, okay, and got that that was 0 units. So this is really 0 over 2, which is 0, okay? And this would be, because we're talking about an average velocity, this would be units per whatever our time happens to be. I didn't give you units in this question, so I'm giving you really generic ones back. But again, think about average rate of change here. If I'm talking about a rock between this point and this point, that line that connects them is just going to be a horizontal line. So it should make sense that your average rate of change is 0. So what is the actual velocity at 2 seconds? This is the average velocity. And again, that average velocity is really adding up like all of these velocities together and taking the average. But the reason it comes out to be 0 is all these positive ones here cancel with all these negative ones over here. Okay, our velocity at 2, we're going to need our velocity function back, which we have up here. We already figured out that our velocity function is negative 2x plus 2. So the actual velocity at 2 seconds is negative 2 times 2 plus 2, negative 4 plus 2, negative 2, and this would be units per however your time is being measured. Seconds, minutes, I don't know. Okay. What that is saying is that if I was to look at this thing, the average rate of change right here, I'm sorry, not the average rate of change, the derivative, the slope of that tangent line would be negative 2, which should make sense from that little sketch that I made. Okay, so these are probably going to be some topics that I think are probably harder than the rest of the stuff you've seen so far. So pay some extra attention to this on the homework assignment tonight. Go back through these examples if you need to, and we can definitely discuss them in class if you need some more help with them. All right, have a great night.